A Roman general's simple letter jumble delayed disaster. 9 centuries later, an Arab scholar broke every secret with just a table of letter counts. From Julius Caesar's battlefields to mathematical showdowns that changed wars and toppled empires, the history behind today's invisible codes is a relentless battle of wits, and every safeguard ever invented has fallen. But what if our digital world is built on puzzles just waiting for their perfect solver? Julius Caesar relied on a simple trick to shield his orders during the Gallic Wars. Each letter in a message was shifted forward by a fixed number, often 3. A became D, B became E, and so on. What looked like nonsense to an enemy hid real plans from prying eyes. Over time, this method inspired mono-alphabetic substitution ciphers, where any letter could stand for any other. The possible combination soared to an almost unimaginable number, over 403 septillion different keys. For centuries, these ciphers seemed unbreakable, their secrets locked behind sheer mathematical scale. But every code carries its own weakness. In the 9th century, an Arab mathematician named Al-Kindi noticed a subtle pattern. No matter how letters were swapped, the frequency of each symbol did not change. In English, the letter E appears about 12.7% of the time, and the most common 3-letter word is the. Al-Kindi created tables tracking how often each letter appeared. By matching these counts to known language statistics, he could reconstruct the original message without ever knowing the key. The longer the intercepted message, the clearer the pattern became. What started as a puzzle of brute force became a scientific battle with statistics. This realization exposed the fatal flaw in all mono-alphabetic ciphers and forced codemakers to imagine new defenses, ones where patterns would not give them away. In 1586, Blaise de Vigenere introduced a cipher that promised to outsmart pattern hunters. Instead of a single alphabet, his method used a keyword to shuffle the code, so each letter in the message was encrypted by a different Caesar shift, cycling as the keyword repeated. A 7-letter keyword meant 7 separate shifting patterns, making the code seem to twist and turn with every step. For nearly 3 centuries, this polyalphabetic system was called Le Chiffre Indecipherable, the indecipherable cipher. Cryptographers believed that changing the substitution alphabet with every letter would finally erase the telltale fingerprints that had doomed earlier codes, but repetition left a crack in the armor. In the 1850s, Charles Babbage noticed that when the same word appeared in the plain text and the keyword lined up the same way, the resulting code blocks would match. Friedrich Kasiski published the breakthrough in 1863. By scanning for these repeated blocks and measuring the distances between them, one could calculate the greatest common divisor, the likely length of the keyword. Once that length was found, the cipher split into separate strands, each vulnerable to frequency analysis all over again. The Vigenere Cipher, once thought unbreakable, fell to the same relentless logic that had toppled its ancestors. Each new layer of complexity brought only temporary safety, as human habits and mathematical patterns found ways to resurface. On January 16, 1917, a secret telegram left Berlin, bound for the German ambassador in Mexico City. The message, encrypted in code 0075 and routed through American diplomatic cables, offered Mexico an alliance. If the United States entered the war against Germany, Mexico would reclaim Texas, New Mexico, and Arizona. British intelligence had been watching. For years, Room 40 analysts had collected German code books and studied their patterns, patiently building a map of the cipher's inner workings. When the Zimmermann telegram crossed their desks, they moved quickly. Within hours, the message was decoded, its promise of land and alliance laid bare. On February 24th, the British handed the decoded telegram to the United States. The impact was immediate and explosive. Newspapers published the full text on March 1st, igniting outrage across the country. American public opinion, long divided about the war, shifted overnight. Less than 6 weeks later, on April 6, 1917, the United States declared war on Germany. A single intercepted message had changed the course of world history. The Zimmermann telegram exposed the danger of relying on code books and repeated ciphers. Patient cryptanalysts could turn years of quiet work into a geopolitical shockwave. In the aftermath, secrecy would demand new machines, new mathematics, and a recognition that information itself could become a weapon. The Enigma machine arrived on the battlefield with an air of invincibility. German engineers packed its circuits with layers of secrecy. 3 rotors spun with every keystroke, wires crossed in unpredictable ways, and a plug board scrambled the alphabet even further. The result was staggering. Roughly 158 quintillion possible settings, reset every day. German command believed their messages were safe forever, hidden behind this mechanical labyrinth. But in 1932, a group of Polish mathematicians found a chink in Enigma's armor. By studying intercepted messages and exploiting careless habits like repeated message keys, they uncovered patterns buried in the machine's output. Marian Rejewski and his team mapped the inner wiring, built replicas, and even constructed a primitive machine to guess daily keys. When the war closed and the Poles handed their secrets to the British, Alan Turing and his colleagues at Bletchley Park took the next step. They designed the bomb bee, an electromechanical brain that could sift through Enigma's astronomical settings at unprecedented speed. The key was a hidden flaw. Enigma never allowed a letter to encrypt as itself. Turing's team used cribs, predictable phrases like weather report or Heil Hitler, to test possible settings. If a crib produced a contradiction, the bomb moved on. If not, the settings narrowed until the daily key fell into place. By 1944, Bletchley Park was reading up to 4,000 German messages a day. Historians estimate that breaking Enigma shortened World War II by as much as 2 to 4 years, saving millions of lives. The Enigma's defeat proved that even the most complex machines can betray their secrets when patterns slip through the cracks. In 1949, Claude Shannon published a proof that seemed to end the search for perfect secrecy. He showed that the one-time pad could never be broken, not by brute force, not by clever mathematics, if its rules were followed. Every message required a key as long as the message itself, made of truly random numbers, and used only once. When applied correctly, the ciphertext revealed nothing. Soviet intelligence trusted this system during the Cold War, convinced their secrets were safe behind the iron wall of Shannon's mathematics. But human nature found a way in. Wartime shortages and pressure led Soviet clerks to reuse one-time pads, violating the single rule that guaranteed security. At a hidden facility in Arlington, Virginia, American analysts working under the Vigenere project began to notice patterns in intercepted Soviet cables. By comparing 2 messages encrypted with the same pad, they could combine the ciphertext and strip away the key, revealing the hidden structure beneath. This technique, taking the exclusive or of overlapping messages, turned mathematical certainty into a liability. Over nearly 4 decades, the Vigenere team decrypted around 3,000 Soviet messages. Their work exposed spy networks inside the Manhattan Project, and named operatives like Klaus Fuchs and the Rosenbergs. The lesson was stark. Even the strongest cipher collapses if its rules are bent. No equation can outpace a single careless mistake. As the world rushed into the digital age, the struggle shifted from inventing unbreakable codes to finding a way to share secret keys without trusting human hands. In 1976, Whitfield Diffie and Martin Hellman published a radical idea. 2 people could agree on a secret key without ever meeting, using only public exchanges. This was the birth of the public key concept. The next year, Ron Rivest, Adi Shamir, and Leonard Adleman introduced RSA, a system built on mathematical trapdoors. Multiplying 2 large prime numbers is easy, but reversing the process, factoring the result, remains out of reach for even the fastest supercomputers. A 2048-bit RSA key, the backbone of modern encryption, would take trillions of years to break by brute force. Today, RSA protects about 90% of internet traffic, from banking to private messages. But in 1994, Peter Shor revealed a looming threat. His quantum algorithm could, in theory, shatter RSA by factoring those same numbers in hours, not millennia. So far, quantum computers have only managed to factor small numbers, up to 21 as of 2024. Yet the race is on. IBM and Google are building machines that may someday wield 20 million error-corrected qubits needed to break RSA at scale. The world is not waiting for disaster. In 2024, NIST selected 4 new post-quantum algorithms: Crystals Kyber, Crystals Dilithium, Falcon, and Sphinx Plus, designed to resist both classical and quantum attacks. Meanwhile, quantum key distribution, tested on China's Mikyus satellite, and the Beijing to Shanghai network, offers physical security based on the laws of physics, though at enormous cost. As governments and corporations scramble to migrate, the cybersecurity market is projected to hit $500 billion by 2030, driven by the urgent need to defend secrets against tomorrow's codebreakers. Right now, nearly every private message, bank transfer, and government secret depends on codes built for today's math, but tomorrow's breakthroughs could expose it all. In cryptography, security is never permanent. It is only borrowed until the next mind or machine finds the flaw. Thanks for watching.